Hello, in this video I want to talk about segmentation and more specifically the detection of discontinuities. Now, the most significant, meaningful technique to detect discontinuity or discontinuities is through the detection of edges in an image. Now, edges in an image are characterized by an abrupt change in pixel values of an image. To give you an intuition of what that is, consider with me this one-dimensional image. So this is my one-dimensional image in the form of a vector that would include 8 pixels. So here I would have 0, 0, 0, 0, and then the change will be sudden from this pixel to this pixel. So from 0 it's gonna change to 1. And I keep writing ones, associating ones with other pixels. And of course I consider here that 1 is the maximum value that a pixel can take. And in this way I would have represented the highest possible change. Now, if you plot this edge, this one-dimensional image, you would get something like this. So here I have zeros, and here I have 1. And this transition from 0 to 1 is my edge. This is of course an ideal edge. This is called an ideal edge because it represents the highest transition or the highest change in pixel values, right? So we cannot have a change higher than 1 from one pixel to another. This is the reason why it's called an ideal edge. Now the question is how to detect that edge. Given an image, how to detect it? Well, we use a simple mathematical operation called derivatives. And this makes sense because derivatives give us the rate of change of an image, and we can use this rate of change to see where this rate is very high and detect thus an edge. Now in discrete level we can use this is a good approximation to detect edges or to get the derivative of an image. We can simply use this kernel that include 3 elements. So here I have 0, here I have 1, and here I have -1. And in order to get edges, we have to convolve this kernel with this image, I. You have to convolve it with this image. And the way by which we do this is that we take our kernel, we put it over our image, and we slide it over the entire image. And in each position, what we do is we perform a multiplication wise between the elements, between the kernel, the values of the kernel, and the values it covers in the image, right? Let me give you an example to illustrate that. So let's say that my kernel is in this position. So this is position 0, 1, 2, 3. Position 3. So now, in position 3, to get the output of this pixel, the output value of this pixel that has an index of 3, what we have to do is to multiply this by this, right? So 1 by 1 is 1. 0 by 0 is 0. And 0 by minus 1 is 0. And at the end, what we do is we sum up all the values we have got, and in this way we get a value of 1. Now, if we do this operation on all the pixels in this image, this is what we would get as an output. We would get an image that has only 6 elements. So I will have here 0, 0. Here I would have 1, 1, then 0, 0. So I said only 6 elements, not 8 elements. So here I would have nothing, just because the mask cannot go outside the image. Of course, there are methods to deal with that problem, but this is not the purpose of that video. So this is my output image after convolving it with this kernel. And notice here that I've got 2 1s, one here and one here. And if I plot this, I would get this function that has a magnitude of 1. Here I have 0, and here I have 0. And in this way, I have detected an edge. And if I do this on my entire image, I would get edges in the white color and non-edge regions with the black color, which are represented by the value of 0.